This is an absolute position encoder, and it's made only from 3D printed parts and printed circuit boards. I'm on a mission to make this work up to 5000 RPM. I think it's possible, but there has definitely been some challenges. A few weeks ago I started using these huge stepper motors for a custom 3-axis CNC machine build. When moving the axes for the first time and implementing the homing switches, I realized that an absolute positioning system would be way more handy. That's when I decided that it's time to build a custom closed loop actuator including an absolute position encoder. In this video, we are therefore going over the mechanical and electrical assembly of the absolute position encoder and discuss the current challenges and possible solutions. First, we are looking into the fabrication of the mechanical parts. All structural parts are 3D printed and use M1.6 screws in combination with heat-side inserts. These inserts have to be melted into the 3D prints using the tip of a soldering iron. The main components of the encoder are the electrical parts. I therefore designed and assembled two printed circuit boards for a light emitting and receiving side, as well as the actual encoder disc featuring a unique pattern per position. For assembling the electrical components, I used a regular soldering iron to assemble the 0603, 0402 and QFN components to the board. By using decent amounts of flux, isopropyl alcohol for cleaning, and high quality solder, all of this goes together quite smoothly. Now that all of the individual components are fabricated, let's get going on the entire assembly. First of all, the bearing needs to get mated with the encoder disc. Therefore, two 3D printed brackets are assembled around the outer bearing shell. This way it can rotate smoothly around the casing shaft. Next, we need to mount the transmitting side of the electronics assembly into the case. This gets fastened with 3 screws. Afterwards, the bearing can be pressed onto the shaft. This already allows for smooth rotation and gives a view on the LEDs through the slots inside the encoder disc. Since everything ran smoothly up to this point, the next step was mounting the receiver including the phototransistors to the case. For this, the position of the mezzanine board-to-board connectors has to be matched, which works out nicely. As a final assembly step, the bearing has to be fixed to the center of the shaft, and the main receiver PCB has to be fastened to the case as well. There it is, a prototype of the encoder mechanically and electrically assembled to the specified design. But there are some issues I discovered as soon as everything was powered on. First of all, the rotation of the center disc is not as smooth as intended. Due to the placement and 3D printing tolerances, the encoder disc does rub against some of the electronic components, which leads to collisions and uneven movement. This should be solvable by tighter tolerances in manufacturing and more careful assembly of the PCB. Let me show you what I mean. Taking the encoder apart again gets us to the transmitter side. Here the current limiting resistors and LEDs are assembled quite crooked and all over the place. Second, the signal to noise ratio of the infrared LEDs measured by phototransistors is not great. Whilst I get detectable signal changes on the direct output of the phototransistor, the operational amplifier does not work at all as intended. Originally, I expected a way larger difference in the current through the phototransistor and therefore wanted to detect the changes with a comparator directly. I will now have to go and reconsider the circuit. My current best solution to this problem would be using an operational amplifier in transimpedance amplifier mode to directly amplify the current through the phototransistor. This way the output voltage is directly driven by the input current through the phototransistor, leading to shorter delay times and therefore higher possible rotation speeds. Whilst the mechanical issues can be easily fixed, the signal processing will take some additional time. If you're keen on finding out my solution before the next video is released, or have your own suggestions on how to fix this, feel free to engage in the comments. See you in the next episode.